So today we discuss about the inverse matrix of a particular matrix. Okay. Yeah. So we are going through the second sub-chapter in chapter 2, which is about the inverse of a matrix. And so we probably studied the inverse matrix in our high school, and the inverse matrix has some matrix that So for matrix A, so if we have a inverse matrix, and then if we multiply that on either left hand side or right hand side, it will generate the identity matrix, right? So that's the definition of an inverse matrix. And then the exact definition of an inverse, I mean, we have to think about the exact definition because we are quite serious about studying this inverse matrix. So inverse matrix is only defined for this square matrix. So if you see these n by n, which is the size of a matrix A, so we only define the inverse of a particular matrix when that matrix is a square matrix, okay? And so the definition of an inverse matrix is some matrix that will generate A into this identity matrix. And then, as I mentioned, so if you found one matrix satisfying this equation, so in this particular equation, we call that matrix as C. So I gave you some matrices 1, 2, 3, 4, 5, 6, 7, 8, 9, which is a square matrix, right? So at least we can discuss or we can talk about its inverse. I mean the possibility of having the inverse matrix. And then I gave you just a one matrix that is this kind of matrix, and then if you multiply it, it's not gonna generate the identity matrix. But let's assume that someone gave you some matrix, and then when multiplying it on the left, and then it generated identity matrix. Okay, and then please please pay attention in the following. If you found this one particular matrix, and then this is actually a unique matrix that generates this matrix into identity matrix, and then also it's automatically true when multiplying the same matrix on the right hand side. Okay, so if we call that as C, and then if we multiply C on the right, and then it will also create the identity matrix. Okay. So again, if you found one matrix that is multiplied on the left, and then that creates an identity matrix, and then if it's multiplied on the right, and then it will also create matrix A into identity matrix, and it's always true. Okay, we will see the proof about it in the next chapter. And then also more important thing that we have to know is, if someone gave you one particular matrix that satisfies this, and then you don't need to find any other matrix because this will be your unique matrix that will generate this relationship. So again, in other words, there is no other matrix, no other different matrix than that creates this kind of relationship. So in short, inverse matrix is unique. So if someone gave you one inverse matrix, and then that will be your only inverse matrix. Okay? So we will prove it in the next chapter and later in this chapter. So back to the definition of an inverse matrix, matrix for a given matrix A, which is a square matrix again. and then someone gave you this matrix C, and then if you satisfy this, and then it will automatically satisfy this, and vice versa. So if someone gave you C, and then if you found that A times C is identity, and then this guy will automatically be true as well. And then the C matrix is called inverse of A, and then C is unique. So this is what I just mentioned, right? And then let's look at the simple proof about the uniqueness of the inverse. So, so the situation is this: someone already gave you one particular matrix C, okay? So that satisfies this. So we can call that as an inverse, and then let's assume that there is another matrix B that also satisfies these two equations, okay? And then, yeah, so B is represented as a B times I. So we just multiply the identity matrix, okay? That still makes a B as it is. And then this identity matrix from the matrix C that someone already gave you previously, and we can change identity matrix into this, A times C, right? And then, yeah, we can change the order of the multiplication. And so B times A times C. And then our assumption was we also assume that B is another inverse matrix. So B times A should satisfy this guy. Okay, so B times A should be identity matrix. And so we have I times C and C. And so from looking at the far left, we are ending up with the conclusion of B equals C. So even though we started from the assumption that B is another different matrix from C, okay, but we are ending up with the conclusion of B equal to C, okay. So that way, even though you try to start with the different matrix, you will always end up with the same matrix C. So that way, inverse matrix is unique. And then, in particular, the notation for the inverse matrix of A is represented as this, right? Okay, for 2 by 2 matrix, you guys know the formula about how to define the inverse matrix of A, B, C, D. And then in particular, this guy, AD minus BC, is called the determinant of A. Okay, and then let's think about this inverse matrix in the context of a linear system. Okay, so let's think about this linear system AX equals B, and then suppose your matrix A is invertible matrix, or your matrix A has an inverse of its matrix. Okay, so A inverse is defined, and then in that case, in order to be able to discuss, or in order to be able to talk about the inverse matrix, the first assumption is the matrix A should be square matrix, right? So here, we only think about n by n matrix, right? And so this situation, first of all, the situation in this linear system is that we have the same number of equation and also the same number of variable, right? So if n is 3, and then this is a 3 by 3, right? So 3 by 3, and then we have another b, right? So we have 3 equations and 3 unknowns, or 3 variables. Okay, so in this situation, if your matrix A is invertible, and then among the 3 possible cases in the linear system, whether we have a no solution, or unique solution, or infinitely many solution, among these 3 possible cases, if your matrix is invertible, and then your linear system will be always having a unique solution. Okay, so let's prove that. So at least let's try to think about the existence of the solution. So at least one solution satisfying this equation will be this guy. Okay, so yeah, the situation is someone gave you x as this guy, and then let's just check, or let's just verify if that is our solution or not. Okay, so you just simply plug this guy into X. Okay, so A times A inverse times B, and then this guy, we change it into identity, and so it will become B, and so that will satisfy this equation. So at least we verified this guy, this solution that someone gave you is satisfying our linear system. Okay, so at least, so just like a homogeneous linear system, even though, yeah, in the case of a homogeneous linear system, we just by default, we just immediately know that all zero, I mean the solution of all zero will automatically or always satisfy our homogeneous linear system, right? So it will exclude out. So it will remove the case of having no solution, right? And then let's check whether we have a unique or the infinitely many solution. Okay, so we have at least one solution, and then let's prove whether we have unique or infinitely many solution. So let's start with another solution, U. So let's just assume that we have another solution, okay? And then that solution will satisfy A times U equals B, right? And then from here, we manipulate this equation by multiplying A inverse on the left side of each equation. And so we have identity here, and so U is A minus, A to the power of A inverse times B. Okay, so it's exactly the same as kind of this scenario. So we assume, we started with the assumption that we have another different inverse matrix, but it always ends up with the same or previous inverse matrix. So it is almost the same thing. So even though we started from the assumption that we have another solution mu, but this solution mu will always have the form of this guy, which is the solution that someone previously gave us. Okay, so we can see that the solution is always unique. Okay, so at least we have one solution, and that solution is a unique solution. Okay, then continuing that, let me discuss another insight about it. So suppose we have 3 by 3 matrix of an A, and then we have to have a unique solution, or we have to always have one solution. We always have at least one solution, right? And then so for regardless of any B, our solution X is always uniquely defined as this, right? So that means for any B, so we will always have a solution. And what was that? What was the situation corresponding to that? So for any B, we always have a solution. In that case, what was our condition or requirement in terms of the pivot position of matrix A? 뭐든? 네. Good. Yeah. So more exactly, the student gave a correct answer. So if you recall the theorem that we learned, we have to have a pivot in every row, right? So in that case, we can say that we always have at least one solution for any B, right? But in terms of inverse matrix, we always discuss the square matrix A, where we have the same number of equations and the same number of variables. So the fact that we have pivots in every row, okay, for 3 by 3 case, how can we have a pivot in every row? So if you think about reduced echelon form, every row has to have a pivot. So one is here, and then the next one cannot be here, and so the possible will be position will be here or here. but we have to have another pivot in the third row. So this, right? So this is the situation where we have pivots in every row, and then automatically every column will have a pivot too. Okay, and so the situation when pivots are, every column has a pivot. What was the related situation? So pivots, so every column has a pivot, and it means in terms of a free variable, do we have a free variable or not? We have no free variable, right? Okay, so so we have no free variable, and so no free variable means we have either unique solution or no solution. We cannot have infinitely many solutions, right? So in this particular square matrix case, so those two different things are actually the same thing. The two different things are, like, the one is we have at least one solution, or we have no free variable. Okay, so no free variable is actually the same thing as we have at least one at least one solution for any b. So that way so no free variable situation is actually equivalent to the situation where we can have always at least one solution. And so that's we will see more details about these relationships in the next chapter, but let's try to keep this kind of insight in mind. Okay, and then let's move on to next theorem. So if A is an inverse matrix, invertible matrix, which means A inverse is defined, and then automatically A inverse matrix is also invertible matrix, and the inverse of this matrix is the original matrix A. Okay, so A inverse of an inverse becomes the same as A, and then A times B, or this kind of product of these two matrices and then its inverse, like this, is the same as the product of each inverse in a reverse order, which means A times B inverse is the same as B inverse times A inverse. Okay. And then this kind of thing can be also understood in terms of composite functions. So if you remember, remember x and then y, where y is defined by A times B, and then y is further mapped into z, where z is b times y. And let's just use b here and then a here. Okay, and then z is a and b times x, right? And so the inverse matrix of this A times B is something like this. X is some inverse matrix times Z. So the inverse of this guy is satisfying this kind of relationship. So what will be this square or this box? Okay, so in that case, so it's mapping X first using B. So B is used first, and then the second step is to transform using A. But in order to send Z back to Y and then further back to X, we have to first map A inverse, and then B inverse in the second step. Okay, so in this question box, this guy should be A inverse and B inverse. Okay, so AB inverse is the same as B inverse and A inverse, because we have to also switch the orders between these transformations, each of these transformations. Okay, then the third relationship is also interesting part. So we discuss, we think about the inverse of some transposed version of the original matrix. So I give you this matrix 1, 2, 3, 4, and then someone gave you its the inverse matrix as this. Okay, so this is clearly wrong, but let's just assume that is an inverse of A. So A and A inverse. Okay, and then let's think about is the transpose, the matrix transpose of a matrix A, which is A transpose is 1. So we draw this diagonal and we flip that around this diagonal entries. So 1, 3, 2, 4, right? Then what about its inverse? A transpose of an inverse. That is actually just transpose of this guy, which is we just transpose it. So this, okay? So that way, this guy's inverse is the same as this guy, and so just writing it as a mathematical equation, this guy's inverse is the same as so I rewrite this part as this, because we just simply did this thing, right? A inverse starting with the A inverse and then did the transpose of it. So A inverse of transpose is the same, okay? So these are transpose. Also this is transpose, okay? This is an inverse, and then these two are also satisfying the inverse relationships. And you can easily prove that, okay? How? How can you prove that? So let's start with this AT, A transpose, and then think about some matrix which is multiplied on the left, and then try to create that as identity matrix, okay? And then, the scenario is someone already gave you this guy as your solution for this equation, okay? So someone gave you this guy is your inverse, and then let's verify if that is true. Okay, so in this case, from here we know this guy. So the property that we gonna use is this guy. A times B transpose is B transpose and A transpose. So we also reverse the order here. Okay, so moving from here, we can change that into this form. Okay, and then this guy has the transpose of each matrix. And so we switch the order. This guy is coming first, and then this guy is coming later. And then we do the transpose. And then here we have an identity matrix. Identity matrix to the transpose of a transpose of an identity matrix is also identity matrix. And so we at least found one matrix that satisfies, when multiplied, that becomes identity matrix. And then at this point we are fully happy, which means we don't need to find any other inverse matrix that satisfies this relationship, because we already proved the inverse matrix is always unique. So if you found one matrix that satisfies this, then that will be your only one inverse matrix. Okay, then the next thing that we will learn is this guy, elementary matrix. So before looking at this example, I'll try to teach you in more insightful manner about it. So what we will learn here is, so let's try to remember what were the three operations in the row reduction. So do you guys remember three kinds of row reduction operations? What was that? Scaling? Yeah, row replacement and scaling and interchanging, right? So interchanging means we just switch between the two rows on a given matrix, right? And then scaling means we pick up one particular row and then we multiply the entire row by some scaling factor, right? Multiply it by 3 or 1 over 3 and so on. And then row replacement was we multiply some row and then add them to another row. So that was, and then we replace that resulting row into the second row. So that was row replacement. So we basically have these three operations, right? And then when doing the row reduction, if you did your homework and also did your exam, then what did we do? We did something like this or something like this. And then, so we multiply the first row by 3 and then subtract it from the second row. Then 1, 2, and then what do we have? 0 and what? What would this number be? So just a standard or typical row reduction. -2, right? Yeah. Okay, so between this matrix and this matrix, we represented their transition or their conversion as this arrow or this kind of weird, weird curly line, right? And then now we will learn how to create an equation where this matrix is A, and then suppose this matrix is, for example, B, and then we represent B as being equal to some matrix, A multiplied by some matrix, okay? And then this matrix is actually doing this exact same row reduction, okay? And then what would this matrix be? So we will learn about this kind of matrices, and that matrix corresponding to each of your row operation is called elementary matrix. Okay, elementary matrix. And then we will actually study the new perspective of matrix multiplication. In the previous chapter or in the previous class, so suppose, let's remember what we learned last time or in the last class. So suppose we have a three columns in a matrix A, and then I'm gonna give you 1 minus 1, 2, and then what's the meaning of so it will. So suppose that each of the column is represented as a 4-dimensional vector, and then the resulting vector is what? four-dimensional vector, and this vector is a linear combination of these three weighted by these guys, right? And then, so we are just reviewing what we learned in the last time. And then what about having another column, maybe 2, 1, 0. Then what is the row of this second row, second column in matrix B? So that will create another column in your resulting matrix. And that column vector is also a linear combination of these three, but using different linear combination coefficient, right? So that's what we learned last time. Okay. Then now we learn another perspective. So in this perspective, the columns of an A is kind of our ingredient, so our basis. So we have initially these three vectors, and then their linear combinations are forming each of our column vectors, right? And then let's start with the second matrix B, and then now consider their rows instead of columns. So initially we started with A and their columns, but now we view this matrix multiplication starting from the second matrix B, but we now consider the rows of B. Okay, so suppose B has 3 rows. Okay, then I give you. So first of all, let's suppose B is just a row vector. And then what is the dimension of that row vector? A. What's the dimension of an A? So we have 3 rows here. And so at least the dimension here is 3. So this dimension should also be 3, right? Okay, so if we assume A is a row vector and that row vector dimension is 3, okay? Okay, then I'm going to give you this row vector as 1, 2, and 0. And then, similar to the previous perspective, the resulting matrix will be the linear combinations of those rows. I mean 3 rows. Suppose 3 rows is V1 transpose, V2 transpose, and V3 transpose. And let's just call the name of the first row as V1 transpose. Okay, that is just the name of this first row vector. And then second row vector is a V2 transpose, and then V3 transpose. And then the resulting vector or resulting matrix is just one single row, and this row is the linear combination of these 3 rows, and then the linear combination weight or coefficient will be 1, 2, 0. Okay, so this guy is multiplied here, and then this guy is multiplied here, and then this guy is multiplied here, and then we just sum them up to form one single row. Okay, and then let's verify that if that is true. So suppose we have, let's start with a very simple case where we have I'm going to use the new page. Instead of this 4-dimensional row, let's simplify this row dimension as just 1. Okay, so each of this guy is corresponding to this. Okay, So we just simplified each vector dimension as 1. Okay, and then that was 3, 5, and 7. And then let's bring this guy on the left. Then it is 1, 2, and 0. Okay. Then we can easily compute this vector and vector multiplication. Okay, but it can also be viewed as this, right? So 3 times 1, and then 2 times 5, and 0 times 7, and then we add them up, right? By just squeezing them vertically, right? And then what if we have another value of 2, 4, 8. So we now extended each row as a two-dimensional vector. Then we will do the same thing. Okay, so the vector is also two-dimensional vector because we started with these two-dimensional vectors and their linear combination. But now we are dealing with the row vectors. So basically, row vector and their linear combination is the resulting output. Okay, so similar to multiplying by 1 and 2 and 0. So we do the same thing, 1, 2, and 0, by applying the exact same linear combination coefficient. That's how we obtain this value, right? And so that way, if we think about their row vectors, and then their linear combinations are our result here. Okay. Okay, so if we start with the second matrix, and then we now consider each of their rows in the second matrix, and that will be our ingredient or our basis. And then their linear combination will be formed or will be the output of matrix multiplication of this guy, A times B. Okay. Okay. So here, back to this example. Okay, by using the columns of an A, and then in the B part, each column was acting as linear combination coefficient. And this guy was forming this guy, and this guy is another set of linear combination coefficient that will generate the second column. Okay, so let's try to extend this A part so that we have another column vector of maybe 2, -1, and 1. So we now have one set of linear combination coefficient, and then we now have another set of linear combination coefficient, and then this guy is creating the first row, and then this guy is creating the second row by using different linear combination coefficient of 2, -1, and 1. Okay, so instead of 1, 2, and 0, which came from here, we now use 2, -1, and 1. That will create our second row. Okay. Okay, and then if you understood this, then we can now build this matrix that represents our row operation, whether it's a row scaling or interchanging or row replacement. Okay, let's start with this 1, 2, 3, 4. So this is our first matrix A. And then we now view them as row by row. Okay, and then let's start with the very simple case of, so I'll use just a little bit different one to make the example a little bit more interesting. We consider 3 by 3, or I'll make it even more interesting by having another row. Okay, so we have this 3 by 4 matrix, and that is our A, or it can be just an augmented matrix. Okay, this could be our A and this could be our B. Okay, and then let's imagine the row operation, and then so row operation should be done so that we can make this matrix as echelon form or reduced echelon form. But let's just do some arbitrary row operation. For example, the first row, the easiest row operation will be just the scaling the third column by 1/7. Okay, and then we would do this kind of operation by 1, 2, 3, 4, 10, and then 5, 4, 6, 11, and then 1 and 8/7, and then 9/7 and 12/7. Right? Okay, then let's call this entire matrix as A. Then we try to make this equation as equal by multiplying some matrix here. Okay, then so in this case, our ingredient row vector is this guy, these 3 rows. Okay, and then we have the resulting row of these 3 rows, right? And then each row is a linear combination of these 3 rows, right? And so let's try to create the first row. Okay, that first row and the linear combination coefficient will be corresponding to the first row of the left matrix, right? And then the dimension of that vector is a 3-dimensional row vector, right? Because we have 3 rows, and so we need 3 different weights associated with each row. And then it will be just the same row of the first row. So we have 3 row vector, and then the resulting row vector is actually the first row, right? And then in that case, what is the corresponding linear combination weight? 100, right? Yeah, that's good. 100, right? So that way we just only pick up the first row without changing it at all, and then we just bring them into the resulting row. What about the second one? Second one is the same as the second one. What about the linear combination coefficient? 0, 1, 0, right? And then that linear combination coefficient is attached in the second row of this matrix E. Let's call this matrix as E. And then let's now think about the third row. So third row is, among these 3 rows, we pick up the first row, we pick up the last row or the third row, and then we just scaled it by 1/7. Then what should the linear combination coefficient be? 1/7. Okay, so the student said 1/7 and 0 and 1. Okay, and then this 1/7 is associated with here, right? And then 0 and 1, right? Yeah, right. So are you guys following it? So it should be 0, 0, and 1 over 7, right? It is because, so we simplify, we simply multiply the first row as 0, and then second one by also 0, and then the third one we multiply it by 1 over 7, right? And so 0, 0, 1 over 7, that linear combination ways are forming the third row. Okay, that is creating the third row. Okay, hopefully it should be simple. Okay, then I'm not gonna give you the exact number. Let's be more conceptual. So we have 3 rows. We don't know the dimension yet. And then now we want to switch between the first and the third row. So for example, 0, 0, 1, 0, 0, 2, and 0, 1, minus 1, 1, minus 1, 2. In that case, if we are given that matrix, and then the first thing that we will do is to change or interchange between the first and the third row, right? So that is our one of the 3 row operation called the interchange. Okay, I'm gonna remove exact numbers. And then let's try to construct this matrix so that we can have that row operation result. And then the first row, okay, I'm gonna make it pretty by using different colors. Okay, so the third row should become the first row. In that case, what is the linear combination coefficient that is placed here?
First row, third row or first row?
Yeah, third row becomes our first row. And what is the corresponding linear combination coefficient? 0, 0, 1, because we are just picking up the third row, right? And so linear combination coefficient should be 0, 0, and 1, right? And that number is placed here, 0, 0, and 1. What about the second row? That creates just second row as it is. Okay, so in that case, what is the linear combination coefficient? 0, 1, 0, right? And then what about the third one? 1, 0, 0, which is picking up the first row and then placing them into the third row. Okay. Okay. So color coding, may not be necessary, but yeah. So that way, the interchange operation can be also represented as another matrix of this kind. So so let's call this matrix as E, and then E times the original matrix A will become our new matrix B. Okay, and then if we imagine doing a sequence of row operations, at first, in the first place, we do some row interchange, and in the next step we do row reduction, row replacement, and then do another scaling and so on. And then we can think about that kind of sequences, right? So in that case, our kind of answer would have been something like this: A, we have some matrix, and then we do some first step of row reduction, and then we have another matrix. Let's call that as B. And then we do another row reduction, and then we call that as C. In that case, B will become, so let's call this row operation and its corresponding matrix as E1. So let's call this as E1, and then the second step and its corresponding row operation as E2, right? And then the resulting matrix relationship is, so suppose C was our final destination, which was either echelon form or reduced echelon form, and that is represented as this equality or this equation. That equation is by just sequentially multiplying row operations step by step. So starting with A, and then we apply the first row operation, and then the second row operation, and the third operation, and so on. Okay. Okay. Then so we are still left with the row replacement operation, which is the most difficult version, but let's think about it in a second. But let's consider this kind of conceptual or this kind of equation. So we can build this equation, and then let's imagine our reduced echelon form. So if A was 3 by 3 matrix, and then if its reduced echelon form was just identity matrix of 1, 1, 1 and 0, 0, 0, 0, 0. Okay? And then suddenly this matrix C, after we do multiple steps of a row operation, that becomes identity matrix, right? So reduced echelon form and the matrix of a reduced echelon form, starting from a 3 by 3 matrix, it became some identity matrix. And so we can replace this I by matrix, we can replace that matrix C by another matrix, identity matrix, right? In that case, we suddenly have some inverse matrix definition. So we have original matrix A, and then even though it's composed of a multiple matrix and their product, but the left part, this part will become some matrix, right, as a whole, and that matrix will transform the matrix A into identity matrix. Okay, so we just did a row reduction, and then just to try to obtain the reduced echelon form. And if that reduced echelon form was happened to be identity matrix, then the sequence of your row operation is actually becoming your inverse matrix. Okay, because that matrix will be just an inverse matrix of A, because when multiplied with the A, it will generate the identity matrix. Okay, so this is probably the key point in today's lecture. And then, let's get back to the last type of a row reduction, and then try to think about its matrix multiplication version. Okay. Okay, and then let's use different size of a matrix. In this time we will think about 3 by 2 matrix. Okay, and so we have 3 rows, right? So these are the ingredients, and so each set of linear combination coefficient should have 3 components or 3 weights. And that way we will create the first row, then second row, and then the third row, right? And so that's how we maintain the same matrix size of 3 by 2, then 3 by 2 matrix, right? Okay, then here let's consider the row replacement step. So in this, I created this matrix as 1, 2, 3, 4, and then I just multiplied it by 5 and then subtracted it from the third row and then replaced it as a new third row. And then it will be 0, and this value will be what? -4. Yeah. Okay, then let's consider this situation where this matrix B equals matrix A multiplied by some matrix E. And then this matrix, let's construct this matrix. Okay, so the first row is remaining as just the first row. It is the same. And then what about the linear combination coefficient corresponding to this part? 1, 0, 0. What about the second one? Second one didn't change at all. So it will be 0, 1, 0, which is our second set of linear combination coefficient. What about the third one? What about the third one? -5, 0, and 1. Okay, -5, 0, and 1. Do you guys understand that? Right? So we multiplied it by 5 and then subtracted it. And so it is the same as we multiplied the first row by -5 and then added it to the third row. Okay? So this is our matrix E that is multiplied on the left of matrix A, and then that will make the same matrix of B. Okay, so that way we now constructed the the entire set of row operations. I mean, 3 kinds of row operations, and then we now understand its corresponding matrix E that is multiplied on the left of matrix A. This is quite an important part. So, yeah, any questions? Okay, then let's kind of do some reverse engineering, or let's if you understood this kind of this relations between the matrix and the row operation, it should be easy. So the situation is now we are given each of this matrix, and then let's think about its corresponding row operation. So in this case, what is that? What kind of row operation is this corresponding to for the second one? Interchange, scaling, and a row replacement. It's interchange between which rows? Row 1 and 2, right? Row 1 and 2, because this guy is creating the first row in the resulting matrix, and then the linear combination coefficient was 0, 1, 0, and then we pick up the second row, right? And then that is a resulting row. And then this guy is picking up the first row, right? And then what about this guy? This guy is, the third one is scaling, right? Scaling. And then scaling the third row, right, by 5, right? What about this guy? This guy is row replacement. What is the target row? So row 1 times -4, and then add it to the third row, and then that will be our new third row. So it's replacing the third row by using these linear combination coefficient. Okay.
If a row vector ABC, row matrix ABC and column matrix XYZ is outer product of the transposes, which one? This one is 행 벡터 ABC하고 행 하면 힘 ABC하고 열 XYZ를
네.
한행 한 열만 있는 걸로 이렇게 곱셈한 거를 트랜스포즈로 부르래요.
Okay, I'll answer here. Yeah, so that's an interesting question. So the question was, so let's consider the inner product between this row vector and the column vector in both three-dimensional space. And then, okay, so first of all, 1, 2, 3.
Outer product transpose.
No, it's called the inner product.
Oh.
Yeah, it's an inner product. And then maybe 3 minus 1, 2. And then you can easily compute it. And then this, I mean, in terms of the size, is giving the scalar. Okay? And then the question was, what if we do the transpose of it? And then this guy's transpose. What is the transpose of a scalar?
Same.
Yeah, it is the same. Because it's still a diagonal entry. So diagonal entry is remaining as the same. And then, yeah, the student mentioned about the outer product. So in particular, that is called inner product. 한글로는 뭐죠? 내적.
내적.
외적 혹은 outer product.
Outer product 외적. inner가 내적.
네. Outer product is something like this, right? So we have three-dimensional vector, and then now, in this case, we can have like a four-dimensional vector, or it can be five or any dimensional vector. So in this case, what is the resulting matrix? I mean the size of it. It's 3 by 4, right? So it's expanding to a bigger, really large matrix. Okay. In that case, okay, then let's think about this transpose. Transpose. In this case, the resulting matrix. So yeah, let's call that as C. Okay, C transpose is, so this matrix as, let's call that as A, and this matrix as B. Okay, and then so originally A times B was C. Okay, so A times B was C, right? And then let's think about the transpose of this guy. Okay, then in that case, it's like B transpose times A transpose, right? So what is that? So this guy was A and this guy was B. So now it's like we bring this matrix and then transpose it. So the transpose of a row vector will become our column vector. It's a four-dimensional column vector. And then what is this guy? This guy is the transpose of an A. And that is this row vector, right? So we basically switch between A and B. I mean the transpose of each matrix. And that will become our resulting, the transpose of the matrix, original matrix C. But anyways, so this is called the outer product. Okay, and then let's move on to the next theorem. So the next theorem is, so we consider the first situation where your matrix A, which is of course square matrix, and that matrix is invariable. Okay, so this is the first situation. And then the second situation is this. Your matrix A, if we row reduce your matrix A, and then suppose that row reduction generated the identity matrix as a reduced echelon form of a matrix. Okay, so A was row reduced to the identity matrix. Okay, so we consider these two different situations, and then this theorem says those two are actually equivalent. So if your matrix A is invariable, which means that your matrix A has an inverse matrix, and then if you try to do some row reduction on your matrix A, and then you will always have identity matrix as a row reduced echelon form. Okay, and also, yeah, conversely, or you start from the second situation, you found your matrix was reduced as identity matrix as a reduced echelon form, and then it means your matrix is invertible. So this is kind of what I already described in this situation, right? So if your reduced echelon form becomes identity matrix, then it suddenly gives you the definition or the equation for the inverse matrix. Something like the product of these two becomes identity matrix. Okay. Okay, then so this theorem is not yet at the end. So it has a further additional statements. So any sequence of elementary row operations that reduce A into identity matrix, and that is also transforming the identity matrix into an inverse matrix. So it's a little bit it's a little bit tricky to explain, but in practice, or when applying this theorem, when solving your homework, for example, probably the new homework will come out, will be out probably later today. Okay, so the question is, given some matrix, obtain or solve for your inverse of the given matrix. Okay, in that case, how you do it is as follows. So I will give you this matrix 4, 5, 6, and 7, 8, 9. Okay, how do the way of computing its inverse is as follows. So we consider the linear system, and then using this matrix A, and then X, and then we need B, right? And then B is 1, 0, 0. Okay, and then this is a first linear system that you should consider. And then the second linear system is that you have to consider. Let's call that as B1, and then B2, and then B2. B1 should be 1, 0, 0. And then B2 should be 0, 1, 0. And then B3 should be 0, 0, 1. Okay, and then you will form this augmented matrix. Okay, and then you now form another augmented matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0, 1, 0. Right? So this comes from the second linear system. Right? So you have to basically solve these 3 sets of linear systems by using the same A, but changing B as 1, 0, 0, or 0, 1, 0, or 0, 0, 1. Okay, but given these 3 linear systems, you can actually solve these 3 linear systems all at once by just constructing one really augmented matrix. So augmented matrix, which is further augmented. So it's like so simply what you do is this. So instead of having just one single B here, you have another B, 0, 1, 0, and 0, 0, 1. Okay, and then how many columns in the place of B that you have? So we basically have 3 B's, which are 1, 0, 0, 0, 1, 0, and 0, 0, 1. But still, you will do the exact same row operations to solve each of these 3 different linear systems, because you will first start from the top left and then gradually moving to the bottom right. Okay, so you will have to handle this part so that this part becomes reduced echelon form or echelon form, right? And then the remaining part, or right part, will just follow. That is applied by the same sequences of row reduction. Okay, and then given this like augmented matrix where we have a multiple B's on the right, And then suppose this guy was transformed or row reduced into this form. 1 0 0 1 1 1 0 0 0 0 like this, and then some matrix such as this. Okay. So in this case, you successfully reduced your matrix into identity matrix, and so that's when you satisfied this second situation, and then this theorem says this second situation is actually the same as the first situation. They are equivalent, which means if you succeeded in changing your matrix into this identity matrix as a row reduced form or a row reduced echelon form, a reduced echelon form, and then at least your matrix has an inverse matrix, and that inverse matrix is this guy. So this is a kind of the most practically useful point when solving your homework. So this part, when going through the same row reduction on this identity matrix, okay, this one will become your inverse matrix of an A. Okay. Okay, so I just gave you the result. Okay, and then let's try to understand why. So we started with the matrix A and then identity matrix here. Okay, so this guy is corresponding to the matrix A, and this guy is corresponding to identity matrix. I just simply wrote that as this one. So this is the starting point. And then we now have a row reduced we now represent row reduction as a matrix multiplication of all these elementary matrices that we learned, right? So suppose we did maybe 4 row reduction by just multiplying like a sequence of 4 matrices, okay? And then what is the resulting matrix? Okay, that matrix is something like identity matrix because we changed it to identity matrix, right? And then let's call the right part as C. Okay, and then this guy, from here we can actually split the single situation as 2 parts, so that E4, 3, 2, 1, and A will become what? Identity matrix. And then E4, 3, 2, 1 times identity matrix as what? C. Okay? And why? Why is that? Because let's think about this matrix A as just one single column. Although they are square matrix, they should be square matrix. But let's think about it as just a column. Okay? And then we have one big matrix. And then we have some columns here. And then they are linearly combined using this way to produce the first column. And then using this linear combination coefficient, and then it will produce the second column. So that way we can have these 2 separate equations. We can split them into 2 equations, right? So in this case, from the first equation, we already know A inverse is what? E4, 3, 2, 1, right? And then what is C? C is the same as this guy, right? So that way, your inverse matrix is automatically revealed by setting up this augmented part by setting up that as an identity matrix, and then the resulting part after you reduce the left part into identity matrix And then the right part will become your identity matrix from this this relationship. Okay, so that's it for today.